Okay, good morning. Today is a continuation of the fast multiple method lecture, but I'm going to introduce the fast multiple in the form of a matrix. So it's the same concept, but this is what happens when you view fast multiple method as a matrix operation. So say that you have like a geometry of 10 by 10 by 10 mesh, like you have a finite difference method. And then what the fast multiple method is doing is it's actually creating A inverse function and doing a matrix vector multiplication against the A inverse. So the original finite difference or finite element method will give you a sparse A matrix, and you will do AX equals B to determine the unknown X, and what you will get is an unknown. Well, let's call it U for this sake. And you can also just, if you can invert the matrix A and multiply it to the right-hand side B, you will directly get the unknown without iterating. And what the Green's function solution using the integral equation is doing analytically is doing exactly this. So if you turn U equals G times F, which is the equation that we've been calculating. If you remember, we were summing a G matrix from point I and point J against some number Q. So you can think of this as the right-hand side F. And this was giving you some answer U. And so what you were actually doing was you were solving this PDE by using an integral form and doing dense matrix multiplication. The reason why people don't usually do such a thing is because if you think of this A inverse, it's a dense matrix the same size as the sparse matrix A that you're trying to solve. So usually you have a big sparse matrix, but it's sparse, so you can solve it without too much problem. But if you do it this way without thinking too much, then you're creating a dense matrix A inverse the same size as your sparse matrix, and then trying to do a matrix vector multiplication on that. So doing that directly is obviously not a very efficient thing to do. But the fast multiple method is not doing the G dense G. It's doing more like a hierarchically sparsified G. So the diagonal blocks of the matrix G are solved in the fast multiple method directly. If you remember this picture here, the P2P part is solved directly. What that's equivalent to doing is the diagonal blocks and maybe the blocks next to them for the neighbors will be solved directly using a dense matrix. But then as soon as you move to the ones that are slightly far away, so these ones that are far away in the geometry in this picture are actually on the off diagonals, so far away from the diagonal, because the diagonal is the close ones. So you can think of the distance from the diagonal as the distance from what you're calculating. So it doesn't map one-to-one because this is a 3D proximity and this is more like a 1D proximity. So the mapping between a 3D proximity and 1D proximity is what needs to be done very carefully. But we use a space-filling curve for that, and that's why we use the Morton index. But you can think of roughly as this distance from the diagonal as the distance in this geometry. And in that case, the analogy of these far big points here are these far big boxes in these areas here. So now you can see FMM that have this shape like this one in the form of a matrix vector multiplication that has a matrix with dense diagonal blocks and very hierarchically sparsified off diagonal blocks. And what I'm showing in this green picture here is the rank of these off diagonal blocks. So a rank of a matrix is, it's information content. And so if you have a big matrix that's dense, you can still have a small rank, like maybe 2 or 3. And in that case, if you apply SVD, singular value decomposition, then you can reduce this big dense matrix into a very narrow, like a tall and skinny matrix and a short and fat matrix like this, times a very small matrix. So you can represent this big dense matrix, so say that this was completely dense and full of numbers. You can represent this with very few numbers, and if you do this multiplication of this times this times this, it will reproduce the big dense matrix. But it's sort of a compression scheme by using just the singular values that are large to sort of compress in a lossy way, but still with controllable accuracy. You can compress any dense matrix to its its numerical rank that is accurate enough. So by using this kind of low rank approximation, the FMM is actually analytically forming this low rank approximation. So think of what this M and L was in now corresponding to this picture. You have, let's call this vector, or it's not a vector, it's like a tall and skinny matrix. This width is not 1, it's actually some small number. And let's call this one U, and this very small block B, and this long block V. Okay, so these U, B, and V things, if you think of what they are in this equation, is that this M is actually this V, and what translates, so this part here, the nabla n plus k times G thing, this thing is this B, and then what you multiply here is the U. So by multiplying these things, you can see that you get the original matrix G, but this truncation number P is now how much you can reduce this B to. So the size of this small block P can be like 2 or 3 or 4, and in our example we're using 1, so what we're actually doing in all the step 1 through step 8 that we did in the coding sessions is actually creating a 1 by 1, like a scalar value here, and then this long vector of 1s, we created a lot of 1s, and then we created another lot of U prime things here. Those were actually these things here. So what we were actually doing is now very clear. We had an analytical equation that calculates the equivalent answer to the singular value decomposition. So without doing any numerical linear algebra like singular value decomposition, which takes a long time, we can directly calculate the content. So every time we do something here, this operation, we get a value without doing any numerical linear algebra. We get the answer of U, B, and V directly. So now you see the correspondence between what we've been doing with the fast multiple method, both in terms of the mathematics and also in terms of the picture, the geometry, what it looks like as a matrix, what it looks like in the geometry, and what this multiple expansion and local expansion meant if you were to do it as a matrix. So there's a one-to-one correspondence. Now, there are a few questions we could ask. So if you can do it analytically without creating a matrix, then why do people want to create or study such thing as a H matrix? The answer is for us to be able to expand G, there were a few conditions. So first, we need to know G, right? Because if we don't know G, we can't calculate this thing here, the gradient of G. So we have to know what function is like an analytical form of the A inverse. You can't always do this. So for example, if you're calculating a Laplace equation or Poisson equation, Helmholtz equation, or Stokes equation, then you know this Green's function solution. So now I reveal why I use the letter G. It's because this is called the Green's function. And this is like a Green's function matrix, which is explicit calculation of the A inverse, actually. So for PDEs that have a Green's function solution, you can do this operation directly. Okay, and there are some other kernels that are not necessarily Green's functions, like radial basis functions or some kernel functions that you want to use in machine learning. So those functions are also a function of the distance, so they have similar properties, and you can sum them like this. But they're not necessarily Green's functions of anything. But still, because you know the analytical form of those equations, you can use this expansion. And so you can still use the analytical way to form these, the compressed low-rank approximation of the off-diagonal blocks. And so this kind of analytical H matrix can be used only if you know the original, forward operator, let's say, of the matrix vector, if you know the matrix vector operator's constructor. So if you don't know that, then what you can do is say that you were handed like some matrix G, that the person who gave you this matrix didn't tell you how they made a matrix G. They just gave you a dense matrix. And you could still do this type of calculation, because you can do a SVD for any dense matrix. Any dense matrix you input, you can just calculate the SVD, and you'll get these, the actual compressed form. So the equivalent of what this was doing analytically, you will be able to do numerically, and you can still construct the same tree structure and have the same kind of interaction lists, and still calculate all the equivalent operations, and have an order n, and this is the important part, you can have an order n method to do this operation. So if you did a dense matrix calculation, then even for just the matrix vector multiplication, you'd have n square complexity to do, because you have n square entries in your dense matrix. And the storage would also be n square if you stored the whole thing. But this one only stores, the order n amount of elements, because basically you're storing proportional to the number of nodes in a tree, and you have n nodes in a tree. And so what you have is a low storage and low complexity way of calculating dense matrix operations. You can view it that way. If you don't know, even if you don't know what G is, you can still view this as an efficient way of compressing dense matrices. So that's more like a black box approach to the H matrix. You're given blindly a dense matrix, and then you have to examine if it's compressible. And you're allowed to reorder the elements of the matrix. So this is something you can do inside the H matrix. While you're doing this compression, you want to reorder the elements in a way that the off-diagonal block compresses well, and this small block becomes small enough. If you reorder it the wrong way, say that you did like a random perturbation of the rows or something, and tried to compress the same thing, applied SVD to this big block here, then it won't compress very well. So reordering is also an important issue. In the same way that we had to do sorting when we constructed the tree. So there's sort of an analogy here as well. So the sorting that we did when we constructed the tree was actually the proper reordering to make this low rank approximation compress more on the off diagonals. That was what was happening geometrically here. So you can sort of map. It's good to know both sides of the matrix form and the FMM, the original geometric form, because you can map ideas back and forth, and you come up with many analogies. So the techniques that have been developed here, a lot of them are not used yet in this area. So there's still a lot that can be done, and I think one of the most significant ones is in the FMM community, when we do this translation operation for the M2L, this distance between x, why do I have this the notation is slightly different from what I've been showing earlier, but anyway, this is like the I prime and J prime distance vector. And if you look at the shape of this interaction list, some, if you have the same relative positioning, so say that you had a different blue box over here, and you were looking at the same relative positioning of the red box. There's always some red box that's in the same distance and same angle as this relation that you have here. So for those ones, this x vector is identical, and so this part, this matrix is identical. And so you have many, many duplicate entries. If you think of the analytical form, it's very easy to see if the vector x, if the relative positioning of the two boxes that you're calculating for the M2L are the same, and you have so many of these inside the whole domain. You have many of these that are just, like translations, but same relative positioning of the two red and blue boxes. All of these, this block B is identical. So you don't have to store all of these copies of the same blocks. And when you look at a matrix that's so big like this one, you can get away by just storing one copy. It's like this one is a lossless compression, say, in memory, because it's just not storing all the redundant information. And in the FMM, there is a way to retrieve, the appropriate copy of the matrix whenever it's necessary. So it's like not storing, but still accessible when it's necessary. So those types of schemes where you can retrieve those, copies without duplicating them everywhere is sort of something that's not used so much yet in this community. For example, that's one idea that can come from people who have implemented this one for a long time, that are sort of looking at this from the FMM point of view. So that's sort of all the analogies. Because I'm showing the two in one figure, it was good to explain everything when I'm showing this slide. Okay, yep. Yes.
So I think the reorder is important. But if I just get a matrix without knowing too much of that, because here we have a geometric view.
Yes.
So we sort of know which should go near us, which should go far.
Mm-hmm.
But if I just have an algebraic matrix, how do I know what is the right reorder?
I think in general, if you just had numbers, you wouldn't be able to just figure out from the numbers. Yeah. You would need some kind of information. Maybe so. Instead, if you were not given the dense matrix, but if you were given, like A, the sparse version first, you can use something like what the algebraic multigrids use. So algebraic multigrid is also it's like a black box way of figuring out the connectivity between the elements. So they just look at the numbers, but they're handed like the sparse matrix, and they look at the sort of connectivity between the elements, and then they do the grouping based on this connectivity. So it's like sort of figuring out the geometry from the matrix in that sense. So they can do it that way. But if you were just handed the dense matrix with a lot of numbers, then there's no way to even figure out, because it's the fully connected part that you're being handed. And in that case, you can't use the connectivity to figure out these things. So you need to ask the person who's giving you that matrix to give you a little bit more, I guess, for you to be able to reorder. Yeah. So if you were given both the sparse part and then the dense matrix corresponding, then you could do something algebraically. But yeah. So okay. But usually, so in the people who do H matrices, a lot of them are doing, so this kind of equation. They know where their dense matrix is coming from usually, and a lot of them, when they try to determine the admissibility, which is whether to subdivide or not the box, when they try to determine this admissibility, they actually get help from the geometry, underlying geometry. So ones that don't rely on geometry also exist, but you need to have some sort of connectivity information for that. So in conclusion, you need something else other than a dense matrix to figure out the ordering. Okay, so yeah.
Yeah, sorry, but this sparsity we based on the connectivity of a sparse matrix. Will that give us a good reorder? Because so it seems that the number doesn't affect how I reorder things. I just look at the connectivity, which means I just look at the sparsity.
Right. So yes, if you're talking about the case where you're just handed the sparse matrix and your objective was to solve, then the typical thing to do is to first minimize the fill-in, by the reorder. So your reordering objective would be to minimize the fill-in, but then you get the Schur complements that are dense, right? So then that part you apply this, and then even for that case, the Schur complement is generated from underlying geometry that you are sort of somewhat aware in that case, because you can figure out from the original connectivity the sort of the underlying geometry of even the Schur complement. And then that case, you're handed sort of a dense Schur complement, but it's not the same as being blindly handed a big dense matrix. So yeah, in that case, you can do something about it algebraically. Yeah. Okay, so and also maybe since this slide contains the most information, so I'll stay on this slide for a long time. So since you've touched upon the subject of using this as a sparse solver or preconditioner, you can, so first do the reordering, like a multifrontal method, and then for the Schur complement, you try to apply the kind of reordering that minimizes the rank. And so minimizing the fill-in, which is looking at the connectivity, and minimizing the rank, which is sort of looking at the distance, is mostly the same, because if you look at this kind of geometry, the connectivity is dense. You have a lot of connectivity where it's near. So looking at the distance and looking at the connectivity are almost proportional. Like if you in 3D, what's connected are the near ones. So you're never connected in this kind of geometry to the far points. So if you want to minimize the rank, you want to minimize the maximize the distance, and if you want to minimize the fill-in, you want to minimize the connectivity, or so it's as long as the connectivity and distance are proportional to each other, it's okay. If you're if you're not looking at some kind of strange graph that's connected to far away more densely, then those two things are nearly equal. The problem is mapping from 3D connectivity or 3D proximity to a 1D proximity. So there's always a point. So if you map this using a space filling curve, which is the way of mapping 3D proximity to 1D proximity, because the proximity inside the space-filling curve, which is a 1D object, is supposed to represent the 3D proximity quite well. But there's always a point where the space-filling curve wraps around and comes back and becomes close in the 3D geometry. But since it traveled a long distance until it got there, in the 1D geometry of the space-filling curve, it's far. So whatever is close in the 1D is close in 3D, but not the other way around. There's always something that's close in 3D but far in the 1D. So there's always something that's close in 3D, which means it doesn't compress, that is far in the 1D geometry, which is in the off-diagonal. So there's always some part of the off-diagonal that won't compress very well, or that you need to subdivide more in that kind of case. So mapping as you go to higher and higher dimensions, you'll see more dense objects appear in the off diagonal. For that reason, it's because you can never map higher dimensions exactly to 1D. If you were somehow magically able to do that, you would be able to very cleanly make larger and larger boxes as you go to the off diagonal. It happens very well in 1D and somewhat better in 2D. But for that reason, using an improper admissibility condition will not give you low ranks in your off diagonals in higher dimensions. And if you're looking at very high dimension kernels, then that's it becomes terrible. Nothing compresses in the off diagonal. So yeah, all these issues arise from the fact that what's close in 3D can sometimes be far in the 1D space filling curve. So yeah, and there's no way to completely map those two. So okay, so this is somewhat repeat of what I've been saying in the first slide, but the HSS is the matrix form. So this is hierarchically semi-separable. So there are many terms here. So I won't go through all of them, but some people call the matrix form the H matrix or H square matrix or HSS or HBS, or there are many names for this hierarchically clustered low rank approximation of the dense matrix. But so if you want to know the difference, there are a few key differences. So FMM doesn't construct the matrix. It actually just uses equations it calculates. Well, you can think of it as a matrix-free operation where every time you construct the entry, you do the multiplication to the vector and you erase it from memory. So you do construct the matrix in the sense that you calculate the entries, but then you throw them away immediately. So you never hold the whole matrix in memory. You just hold them one element at a time. So it has low memory footprint. So you can handle potentially much bigger problems. And then it has higher arithmetic intensity. So if you're calculating on GPUs that prefer higher arithmetic intensity, then these will give you more flops, basically, because they'll be compute bound on your GPU. And then for the matrix version, it stores the matrix. It does very similar calculations, but then it stores the matrix. So if you have many right-hand sides or many vectors that you want to multiply the same matrix to, then this one will have to recalculate the entries every time you want to apply. So it would potentially be wasting a lot of computation. However, this one will just store the matrix. So if you want to just apply it many times, or even like do like a LU factorization or Cholesky, and save that factorized hierarchical form, and just keep applying many times, then in that case, this is very useful. So you need to choose which one based on your objective. So if you're solving a scientific problem that requires just one factorization and then many applies, and I'm talking about like thousands, then this will become very fast. So yeah, then you have different types. When I say admissibility, you can think of it as how much you're subdividing the blocks. So this one divides more. It's called like standard or strong admissibility. And the weak admissibility means you're only dividing like once, and then you go down and immediately divide the diagonal only once, and then once. But this one, you divide, but you divide this off diagonal again and again. So it's more subdivisions in the off diagonal. But this is the part that allows you to sort of handle higher dimensions and still have low rank. So you'll have more boxes with low rank, and I'll discuss briefly about the balance between having more boxes and having higher ranks. And there is a optimal way of determining that. So there are more advanced techniques recently, that sort of nest the hierarchy so that even for higher dimension problems, you can have a faster scheme. So the naive one had very high ranks in the higher dimensions, like if you did a 3D problem. But now you can sort of nest the compression so that these parts that didn't compress, you're going to compress in a different way. Also, there were some, so the original FMM could only handle the matrix vector, the forward operator. But now you have something like the inverse FMM, where you can handle the inverse operation with the FMM form. So not like necessarily creating and storing a matrix. So it still has the low memory footprint feature, but it allows you to use it as a solver now that you can calculate the inverse. And so some of the limitations, like I mentioned, are you need to have numerically low rank of the off-diagonal blocks. Otherwise, if this is completely dense, then this is not a fast method at all. It's just partitioning a dense matrix for no good reason. Okay, and this one requires an analytical form. Like I mentioned in the previous slide, it doesn't necessarily have to be a Green's function. It could be some radial function, but even if you use these kernel independent or black box type methods, you still need the analytical form of the forward operator to start with. So without that, just given a pure dense matrix, black box without any information at all, then you cannot do this kind of geometric variant. So those are the two differences. So in most of my lecture, in the like the past 4 days, I've just been talking about this one, but now you know the relation between, like since this is a linear algebra course, I'm now coming back to a linear algebra representation of what the fast multiple method could be. And I'm trying to carefully give you, the information of when it can be useful and when it won't be useful. Okay, a little bit more on the admissibility and the real reason why this one doesn't compress well for higher dimensions is that if you use this kind of weak admissibility and don't divide the box too much, then you're actually looking at your direct neighbor. So you have white boxes immediately next to you at very small levels, and even at the big levels. So the one that's immediately next to you is trying to be compressed. Here, the boxes that are immediately next to you are actually handled in a dense form, and it sort of skips the immediate neighbor, and then you sort of have only the far boxes being compressed. So you can think of that as only having targets far away from the source. In this case, multiple expansions, and these two are the more algebraic forms, so the matrix way of doing it. They both decay. So this is like the error, and starting from like 10 to 0, minus 2, 10 to the minus 4, 6, 8, 10, 12, 14, and here's where you hit like double precision limitation of like round off. And then this is the ranks. So if you use more ranks to represent, or more terms in the multiple expansion in the multiple case, then of course your answer gets more and more accurate. But it levels off when you hit like 10 to the minus 16. But if it's far enough, then all of them converge. The problem is when you're doing this kind of approximation and you're saying, I want to compress my immediate neighbor. So then you're looking at points that are as close as this one, and then you have these corner elements, so it's not like you're dealing with two concentric circles. This is more like a square, and so this one, the distance from the center of this red point is actually further than the distance from the center to this blue point, for example. And so in that case, the multiple expansion, because the rule for the Taylor expansion that I explained in the first few lectures was that the red point had to be closer than the blue point. That was like the term in the Taylor expansion to be less than 1. If that's larger than 1, then you keep taking the power of a number that's larger than 1, so it's going to slowly diverge. But if you're using singular value decomposition numerically, you can still manage to converge slowly, but still, it does, the error does slowly get smaller and smaller. But the rank that you need to use is like 150 only to get like 6, or no, a little bit more, 7 significant digits of accuracy. You have to use already 100 terms. So it's like a unreasonable amount of ranks that you have for this off-diagonal block. So basically it's not compressing and you're not saving too much computation or storage by doing this kind of weak admissibility. But so there are advantages. Again, I need to be fair and mention that there are advantages of doing this kind of decomposition. So first of all, if you think of actually factoring this thing, or like inverting or doing low rank updates, the structure of, the recursive structure of taking, like the inverse of these decomposed blocks is much simpler for this. If you tried to invert in a block nested structure, this kind of structure, mathematically it's going to look very, very complicated. And so when you're thinking about inverting this structure, having this weak admissibility is much easier. So if you can come up with a way to compress your direct neighbor efficiently by nesting like a hierarchy, then you can have potentially a much simpler mathematical representation of the inversion structure of the hierarchy of the inversion structure would be much simpler. So so there are advantages and disadvantages to both methods. But so for people who have like already a fast multiple method code, yeah, it's the inversion of the structure is not so much of a problem. So for those people, maybe it's not, they prefer to use this one. So okay, now well, maybe I already mentioned this. So I'm just trying to map the terminology between the two, because if you read a paper that says HSS or H-square matrix, it's going to tell you the same thing in a very different way, and you might get confused. So following the equations that I showed earlier, I'm just trying to map here what the correspondence is between these different namings of the same thing. But so I won't go, like explain one by one. Maybe if you're interested and if you're reading the two papers, you can look at this slide because it'll be on mine. And then when you're reading the two papers, you can do the comparison. So just to be clear about the naming of what H matrix is and H square matrix is and HSS and HODLR matrices, Ambikasaran and Darve do a nice summary of the low-rank structure. So the strong low-rank structure or weak low-rank structure, or so the strong one is the one that had less division of the boxes. The weak one is the one that had more division of the boxes. So the two pictures that I showed in the previous slide. And so these ones that have like the light purple colors are not dividing the boxes too much, but the dark purple ones are dividing more. The nested basis is something that differentiates between the tree code and FMM, for example. So if you look at this picture, if you remember, this is a direct n-body. Nested basis means this one. Non-nested basis, like no, is this picture. So the tree code has nested, non-nested basis, and the FMM has nested basis. So you can think of these two methods, Hodler and H matrix, as having this kind of shape. If you look at the clustering of the source tree and the not clustered target tree, the not nested target tree. And then you can view HSS and H square as this kind of structure. Of course, this is, this picture is not entirely accurate. It's just a sketch of, sort of the notion of whether it's clustered or not. Of course, these 2 points need to interact directly, so there should be a line that goes from here to here. And there's more, if you want to be accurate, there's more lines that should be drawn here. But this gives you the idea of what these different representations of the matrix versions are. This is another diagram that sort of shows you, this says FMM in this red circle here, just in case you can't see. But this is sort of the categorization of the different names you may encounter when you actually try to study this area. So if you get confused about what means what, then just look at this slide and it'll be very clear what the correspondence is between what is what. And so the FMM, as I've been repeating many times, it takes a geometrical point of view for this hierarchical low-rank approximation. HSS you can think as like a numerical linear algebra point of view, because this was developed by numerical linear algebraists like Chandrasekaran and Gu. So they are like the in the field of numerical linear algebra experts. So they come from that viewpoint. H squared matrix is more like an operation. So this comes from the German school. Like Hackbusch was one of the the initial developers of what is now called the H matrix. He used to work on fast multiple methods or panel clustering methods a long time ago, and then so a lot of the people that now work on these hierarchical low-rank approximation matrices have in the past worked on fast multiple methods, and so now everyone is trying to generalize what they know to be a very efficient operation and try to extend their field of application. And so you can see the sort of diversity of namings and notions coming from the fact that they were studied from completely different groups that didn't really cite each other initially. But now everyone is citing each other. So the culture is that people from different fields are also aware of each other. And now that people post on their papers on arXiv very frequently, you can immediately see what other people are doing. And it's a good synergy between the different people with different backgrounds. Now we can actually talk and understand with each other and have completely new ideas that were obvious to the other person but not so much to you. So it's an interesting area where everything is intersecting, because n-body people didn't used to talk to like numerical linear algebra people, and they wouldn't go to the conferences, but now you see like people going to the different conferences, and it's an interesting cross-section of everything that's hierarchical and low rank. And so let's see. Yeah, I still have a little bit of time, so I'm going to explain a bit about what happens inside the kernels. So I've explained that the FMM does these operations P2M, M2M, M2L, L2L, L2P, and P2P using these equations here. And there were different ways to calculate this expensive part, the M2L translation operation. But so there exists the same kind of variety in the matrix form as well. So to do the compression of that M2L translation operator, so these are the geometric ones that I explained earlier. So you can do it with like spherical harmonics, with rotations or plane waves or equivalent charges, and using FFT to calculate them. But now for this side, you can use basically like QR decomposition or LU decomposition methods and some randomized techniques. So these are just pivoted versions of the LU and QR. And ACA and HCA are methods which have lower complexity, but sometimes these methods fail because they don't look at all the elements. So it's not randomized either. So they have like a systematic way of examining the dense matrix and to extract the low rank properties and go like why it's called the cross is because it sort of moves in like a, this way and then this way. So it looks like a cross the way they try to find the next elements to look at. So all of these methods you can think of as like purely algebraic methods. And so they have a lot of memory storage, and they need to store the matrix. And then you could think of these methods as like purely geometric methods. But since I mentioned some techniques like storing the same matrix with the same relative positioning, and just using translational invariance to save the redundant copies. You can also use symmetry. So sometimes a lot of these translation operators are like the same or just switch the sign when you move them 180 degrees. So you can use this kind of rotational symmetry, or like if you change them 90 degrees, they also have like other properties, like they could be like the complex conjugate. So you can use symmetry to further sort of cut the storage. And so you can use all these various techniques to also the algebraic side to reduce the storage. But so also these sampling techniques like the randomized versions, and also you can think of these equivalent charges as some sort of sampling technique too. So there are, it's not just binary. It's not like either you're geometric or algebraic. There's some intermediate points where these methods sort of can be combined. And looking at this kind of roofline model for the different architectures, having control over like the memory and how much you compute is very useful, because you can change where you are in this chart. You don't necessarily have to say FMM is here or FMM is here. FMM and the hybridized FMM H matrix can be anywhere in this chart. It's actually controllable. So if architectures shift towards ones that prefer this direction for some odd reason, then you can have control to go this way as well in this picture. So I'm just showing you that this, when you want to develop such methods, there's a whole catalog to choose from, and you can some are difficult to code and but are very fast, and some are difficult to code but are not very fast. So you need to be careful which ones you choose. So in the hands-on session today, I'll try to use step 8 that we left off last time and add a proper kernel so that you have controllable accuracy over it. I won't necessarily give you these kernels here, but I'll make it possible for you to just swap the different kernels in the code. So maybe step 10 will be a kind of code that you can change just this part and it will still function without changing the rest of the code. So once you have this, I think it's a good sort of final code to take home from this whole coding session, because now it gives you the freedom to experiment with more advanced techniques when the time comes. So okay, this is not really necessary for. Okay, so yep.
Sorry, I think you just mentioned that a randomized SVD is sort of equivalent to the equivalent charge. Is that?
No, it's not equivalent. I'm just saying they can both be thought of as some sort of sampling-based technique. So randomized SVD is a way to sample the dense matrix so that you don't have to do an order n square operation to do the compression. So you can have a much better complexity method for doing the compression phase. And so for the equivalent charges, they are actually taking points instead of so if explain to you what the equivalent charges are, I should show you like this picture here. So these points have, inside the center of the box, you have the multiple expansion. But the equivalent charges actually place the points on the edges of this box. So it's actually outside the box a little bit. And you place like a fake charges there that will reproduce the effect of the multiple at the center. So it's like you're taking and the charges that the strength of those charges that you put there are sort of like sampling. So you can either invert a matrix that corresponds to the strength of so if the forward matrix is calculated from the forward equation, you can actually invert this matrix to calculate the equivalent charges that form that potential. So it's sort of like solving the inverse problem to create the equivalent charges on a given point that you give yourself. And so you're trying to find like charges that will represent your multiple well. And an extension of that in higher dimensions, like the code ASCII will calculate those equivalent charges not by inverting this thing, but it actually, because it's in high dimensions, it takes the actual points in the space that exist in very high dimensions and just uses those as sample points. So in that sense, it's sort of can be thought of as a sampling technique. And yeah, so basically that's why I said these equivalent charges lead to the idea of sampling eventually. So yeah, I'm not saying that this thing and this thing is the same. So yeah, it's.
So for the randomized SVD or truncated SVD, I think that's a sort of a truncat of a low rank approximation.
Yes.
So in the FAM side, I think there's some kind of control of degree of the Taylor expansion.
Yes.
Roughly.
So it's also a truncation. So yeah.
I see. But by introducing the randomized, then how can we correspond that to the truncation of the Taylor expansion? Because if you truncate that, that's a sort of deterministic.
Yes.
Yeah. So.
Well, so yes, by nature, this method is not determined. I mean, there's some possibility of failure. It's just that it has been proven to, the possibility of this failing is what was it? Like a very, very small number that's so low that your computer is more likely to break before that possibility. So like computers themselves are not perfect either. They have these things that do memory correction called ECC, but inside the computer is actually failing. If you take it to space, it fails even more. But because the bits flip from the rays coming from space, and so the possibility of this failing is much lower than that happening on Earth. So as long as you're using a computer, the possibility of this failing is negligible compared to the computer failing. So as long as you're using a computer, this should be fine. In the same sense that aiming for a precision that's lower than double precision accuracy is not something you usefully do on a computer. Aiming for a more deterministic method for your higher, lower probability of failure for this one is not really needed at the moment. So yeah, then we can. I wanted to, because I've discussed all these things, here is something that I can explain now, because now you know that the well-separatedness is called admissibility in the matrix form. It's how much you divide the boxes. Because if you divide them more, you have small boxes that are relatively far, which means the well-separatedness is very, very good. In that case, you call it strong admissibility. And the order of expansion is called rank in the matrix form. So there's a correspondence between these two things. Now, you can think of, maybe some of you have heard of HP finite element methods. This is an analogy to HP FEM, and I changed the E to M. So now, H is like a distance-based, so it's like a, H in the finite element methods. It's a criteria of that's associated to the spacing of the approximation. And P is related to the order of, the accuracy that you're expanding to. And then, so in the same way that control of both of these was useful in the finite element community, having control over both of these is useful. And so usually in the geometric fast multiple methods, you don't change H. In the matrix form, the admissibility is determined until, so you sort of keep subdividing the boxes until you get a certain rank. So this H is sort of dynamically determined. So in FMM it's static, and in H matrix it's dynamic. So there's a difference there. But there are methods in the FMM to make, this one. This one has like spatially varying admissibility, even in the geometric FMM. And so what happens is you can either change this or change this to get the specified accuracy, like I mentioned. It's like, well, I was using theta here originally. So I was saying theta to the pth power was the order of the error. But now I'm using h instead, just for this analogy. So you can say h to the pth power is the order of the error. So you can either decrease h or increase p to get a higher accuracy. But now, if you can control the error by changing h spatially to get the target accuracy, then you can have p constant. And you can do the same for the on. And doing AVX was very fast. And also on GPUs, the width, the SIMD width is like 32. So it's much larger than the 8 of AVX. So we want things to be very aligned. And if you have variable rank, so say P was like 32 here, and it aligned very well with the GPU warp, and it was like 8 here, and it aligned well with the AVX SIMD vector width. But in some other areas, say that it was like 5 or 1 or 2, so if it varied a lot in space, then you wouldn't be able to use the SIMD operations very efficiently. So this is something that becomes a problem only when you're doing very advanced coding. But eventually you want your code to be highly optimized. So when you're thinking about the design of your algorithm, you want to consider the fact that if you can achieve the target accuracy by spatially varying h, like you do in the H matrices, then you can have a constant rank everywhere. So then you can have a very SIMD-friendly code. So if, for example, you can set p to a constant of 32 and worry about the target accuracy by just spatially varying the spacing, the admissibility, or the size of the box, basically. So the size of the box you change, but everywhere you have very good GPU usage because the rank is set to 32 everywhere, for example. And so this kind of HP FMM is actually useful because of the SIMD stuff that's coming. And in the future architectures, like I mentioned, there's going to be more and more speed up by being able to use SIMD. So you need to be aware that there is a way to make it faster for these machines. And yeah, I have, okay, so maybe I'll take a break now because I don't want to run too much over. There's not too much more to explain. I'm just going to cover a few more topics. This one and this one. Yeah, this is my last one. So like 4 more slides. And then we can move to the hands-on. I want you to be able to finish coding the proper FMM with the high order terms by the end of today's hands-on. So I think we will start the hands-on a little bit early. And so, yeah, I'll go and continue the last few slides in the next session in 10 minutes. And then we'll do the hands-on and finish the coding for high order FMM. Okay, thank you.